Okay. Okay. Or I should say predict what the label is. So my task is to is given a new feature vector. Who is that? It sounds like me. Okay. Okay. Given a new feature vector for a new patient, attach a label, which is a prediction whether that new patient will develop heart disease. That's my task. Okay. Now, what machine learning is machine learning is your black box that takes your data and produces a model. And you use that model to predict the new patient's outcome. Okay. So really you should think of that what machine learning is. And if you're not a mathematician, then this really is how you should think about it. You should try to see the big picture and let AI take care of the details for you. Okay, okay, okay. That takes this data, okay, and produces a model. Okay, okay. Once you've produced the model, this model will take feature vectors as input and produce a label, which is a prediction as output. Okay, so that's what machine learning is. Whoops, what is this? I didn't ask for that. Okay, 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 okay. All right, okay. All right, so this is the idea. Okay. Now, the details of this is what I will be talking about over the next, maybe this presentation and subsequent presentation. How this works, what you have to do to these this X to this feature data, and how you use this feature data to create this model. You have to do something. You have to split the data. You have to do some various things. Okay. But again, I want to look at this process from a very top level so that you don't need to be so concerned about the details. All right. But this is the basic idea. This is really what's going on in machine learning. Okay. So having this example, let me go back over my presentation, and I hope this will help you make sense of my presentation. So keep this example in mind. It really is we're not just doing some theory, we're doing something very practical. Okay. Not here, I want to go here. Okay. Okay. All right, so here it says that machine learning is about finding patterns in data. Now, how does this relate to what I mentioned? The machine learning process will look within the feature vector and try to extract patterns that indicate whether the patient will have heart disease or not. Okay. So for instance, it might have elevated white blood cell count and blood pressure or something like this, some relationship between the variables. Okay. All right. Now, machine learning, there is two broad categories. And by the way, some people who know something about machine learning may be wondering, well, what about supervised and unsupervised machine learning? I'm talking completely about supervised. I will not talk about unsupervised. So don't ask me questions about unsupervised. We're doing supervised. What does supervised mean? Supervised means that you have data with labels. Okay. You can also do machine learning with data without labels. That's unsupervised. But what we're talking about is data that has labels. And where do the labels come from? The labels come from you. You have to supply the labels. Okay. All right. So two broad categories of machine learning. One is classification and one is regression. But they're really quite similar. The only difference is that classification is attaching a discrete label or an integer. In my case, I attach 0 for no heart disease, 1 for heart disease. This is classification. Regression is predicting a number. Suppose I have weather data and I want to predict temperature. Temperature is a continuous number with a decimal. That would be a regression problem. Okay. So that's really the only difference. Now, in medical, you do typically want to do classification. In epidemiology, you typically want to do classification. Sometimes you want to do regression if you want to predict disease rates or something like this. But typically, you want to do classification. Okay, so in my tutorial, I'll be focusing on classification. But really, the same techniques apply to both. There's also the aspect of prediction versus causation. In my example, we were trying to predict what was going to happen to the patient in 5 years. But you can also ask, what will happen to the patient if I do something? I change his diet, I ask him to do exercise, I do some operation, something like this. Okay. This is a question of causation. Okay. That's a different question. The prediction question is much easier than the causation question. So we will start with prediction. All right. All right. So here, as I said, this is the same idea that you do not need to understand what's in the model. You can treat it as a black box. Now, some of you who are interested in the maths aspect and want to develop better models, you do need to understand. But those of you who just want to use machine learning in your scientific practice, you really do not need to understand what's going on inside. I like to compare with driving a car, right? You drive a car, you have no idea what it's doing. The engine is going, it's burning gasoline. You don't know chemistry, you don't know physics, it's just going, right? You get in the car and you turn it on and you drive it, right? So the same thing with machine learning. You need to know how to get in the car, turn on the ignition, and turn the steering wheel, okay? And that's what I'm going to be focusing on during this training. And you can go deeper yourself. Okay. All right. All right. But you do not need to know some things. You do need to know some things. You need to know what kind of outputs your machine learning model will give, what data it works best with, and how to evaluate and interpret. So these are important. You want to know how to know whether the model is good. The same kind of thing if you go to buy a car. You want to know, well, is Toyota good for this? Is Camry a good car? Something like this. Okay, so these kinds of things you do need to know. Okay. All right. Now, there's this part here that talks about there's two broad categories. Whoops, sorry. Let me go up. Oh, this is sorry. I'm back too far. Okay. Yeah, I'm back too far. Okay. All right. So here again, I talk about the black box. The features, that's your X. The model, that's your black box that is produced by machine learning. And then your prediction is you try to attach a label. And that's really what machine learning does. All right. Now, there are two broad categories of machine learning models. One is called, you can call regression based. It has its roots in linear regression. And I can generate this figure. Sorry, sometimes I give some asides, but last time there was a question over here about when you go home, can you do this programming without a connection to the internet? And because I know all of you are concerned about the cost, there is some cost to, of course, you have to pay for internet. Now, I would say that if you do want, and I also made the point yesterday that you really, really need a connection. You cannot make progress without an internet connection. So one thing you can do is work at night. And I say that seriously because you know from 12 a.m. to 12 midnight to 6 a.m., the internet rates are very low. I think you can get 1 gigabyte for 200 naira. So it's true. I mean, if you're really dedicated to this, you may have to change your schedule. Okay. Isn't that right? I think you can get, I looked online this morning, they said MTN, you can get 500 megabytes for 75 naira. Is that true? But you look, so I don't know what the exact rate is, but you can certainly get cheaper internet at night, much cheaper internet at night. I think in some packages they have they have bonus internet at night. So you may consider, if you are serious about machine learning, you may consider changing your working habits. Sometimes it's a price you have to pay. The other thing is there are some things you can do with your notebook to reduce the bandwidth that's required. And one thing is try to eliminate figures from your notebooks. Instead of putting the figure in the notebook, have the notebook save the figure to your drive. And I didn't do that to this notebook, but in the later notebooks in this series, I changed it so that there are no figures in the notebooks, but the notebook will save the figure to your drive. And this way, it will reduce your bandwidth. Okay. So I will try to be sensitive to your needs, but really, internet is really unavoidable. Okay. All right. So I did run this cell. I generated this figure. You can generate the figure yourself. I have the figure in my drive. I can show it to you. Oh, it's not that. Sorry, it's not that. That's my work. Let me open this. Let's see where it is. All right. Yes, this is it. Whoops, where'd it go? All right. Can I zoom this? How do I zoom this? Like this? I should be able to zoom in. Well, anyway, you may be familiar with linear regression. Linear regression will try to fit a line to data. It will take data and try to find the line that fits this data the best. Oh, yeah, good. Oh, you do it that way. Yes, okay. All right, thank you. Yes. All right, yeah, so there's linear regression right there. Now, in this case, you're only fitting one variable. Whoops, that's the next one, right? Go back to this one. Yeah. Okay, good. So I'll try to do that. Right. Okay, yes. In this case, you are fitting one variable y to one variable x. But in multilinear regression, you may fit one output that's a function of several variables. So you would have several inputs and one output. Okay. And we can call that a neuron. That function that takes several inputs and produces a single output, we can call that a neuron. Now, linear regression produces a linear output. There is also a type of regression called logistic regression. Who has used logistic regression? Any statisticians here? Okay. All right. I think we have two people use logistic regression. So logistic regression doesn't produce a linear output. It produces a nonlinear output. So you have several inputs and one nonlinear output. Okay. So you see that we're building on the idea of regression. Now, what is a neural network? A neural network is simply several logistic regressions linked together. It's a huge array of logistic regressions. Typically neural networks are arranged in layers, not always, but typically they're arranged in layers. The first layer is called the input layer, where you put in your features. So in this case, say we might be trying to predict malaria incidence based on population demographics, region, wealth, education, age, right? So those features would be inputs. They would be numerical inputs. Region, you might label them 0, like you have northwest, southwest, south, south, and so on. You would label those 0, 1, 2, 3, something like this. Wealth, you might have 5 wealth categories. Education also, 4 or 5 education categories. Age categories. So you would have, in this case, you'd have 4 different numbers. And these 4 different numbers are all sent to all of these, what are called nodes. This is the first layer. So these are the inputs to your regression, your nonlinear regression. So each one of these performs a nonlinear regression. The output of that nonlinear regression for each one of these nodes is sent to all of these nodes. Okay. So you have layers and layers and layers of nonlinear regression. And it turns out that you can model very complicated relationships between your features. Okay. So you can uncover very complicated patterns. And then finally, you have the output. The output will be your label, or your predicted label. It might be 0 or 1. It will probably be a number between 0 and 1 that indicates how certain you are about the label. If you output 0.9, then you're quite sure that the label is 1. If you output 0.5, you're not sure if the label is 0 or 1. Okay? So this is a picture of a neural network. Okay? So neural networks are based on the fundamental idea of regression, building up from basic regression building blocks. Okay? That's one kind of model. Another kind of model is a tree-based model. And I have that here. And this is based on a basic structure called a decision tree. Okay. All right. So in this case, here it says we have a decision tree for predicting under 5 child mortality. Now, if you look at the rough characteristics of this, you can see there are several boxes and lines leading from those boxes. Right. And you can see the arrows. Each arrow is labeled true or false. So each box represents a decision based on the data. Now, if this decision is based on a numerical criterion. For instance, this first decision says wealth quintile less than or equal to 4.5. Right. So what does that mean? So we can go into quintiles, but that's a characteristic of the data. You look at one data row, one feature vector, and you decide whether or not that feature vector satisfies this criterion. And now it looks like in this case, 88% satisfy the criterion and 12% do not. If that criterion is true, you go this way. What does that mean? You go this way. That means you take your feature vector and you apply the next criterion to that feature vector. So you look at the feature vector again and say, okay, does this feature vector tell me that the maternal age of the child is less than or equal to 28.5? And it looks like what happens if for those who satisfy this criterion, 86% survive and 14% do not. Okay, so based on this decision, if this criterion is satisfied, I go this way. If not, I go this way. Okay. So I work my way down the decision tree. Okay. So for each feature vector, for each patient, for each child, I work my way down the decision tree. And each child will fall in one of these final categories. Okay. Right. So, for instance, if the child ends up in this category, we can see what happens. So here it says samples equals 18%. That means that 18% of all children fall in this category. And this says value equals 0.9 and 0.1 means that 90% of these children survived and did not die. So the mortality rate for these children is 10%. Okay. Right. Now, if I look at a different category, you can see in this category, the mortality rate is much higher. Okay. All right. So if you have a child that falls in this category, the child is much higher risk. Okay. So this is a way of quantifying the risk of children and doing a better job of quantifying than just getting one number for the child. It's a data-based decision for the mortality probability of a child. Okay. Now, this is a single decision tree. Just like in the previous case, where we took one logistic regression and repeated it to produce a neural network, we can also take decision trees and copy them. So the very high performing machine learning algorithms that are based on trees involve many trees, not just one. You may take 1,000 trees, and each decision tree will come up with a decision. And then you use the decisions for all of those trees and pool them together. So that basic idea is called random forest. You know, forest is composed of trees. And here, because there's some randomness involved, it's called random forest. A modification of that is called XGBoost. XGBoost is, right now, is the gold standard for tree-based models. But maybe in a few years, they will come up with a new model. But the idea is the same. It's still based on trees, still based on these decisions. And the construction is optimized. Okay, let me go back here. All right. So I'm going to pass by this. Okay. All right. So here it talks more about tree-based models. Now one thing about decision trees is that it's very well based for health data, because health data, it's easy to take some health features and apply criteria to them. It's also easy to interpret this model because you can see exactly which criteria are influencing the final decision. Okay. And they can capture very complicated relationships. So that's a good thing. All right. All right, so here we're going to actually do a tree-based model. All right, so let's go down. So if you have it open, I think you can go ahead and you should be able to run this. Now, I mentioned before that when you run a notebook, you cannot just start running in the middle. If I start running this here, I may run into a problem. Okay. And the reason I ran into a problem is that it's going to tell me, whoops, sorry. I don't know why. It's going to tell me what? Okay, actually, this has another error. Uh, so in this case, the font size parameter. So we need to change this. So this is an error that you could debug with machine learning with AI. I'm going to fix this error for you. If you read this error here, it says the font size parameter of plot tree must be an integer. Okay. And it says got 9.5 instead. Now, if you think about what this means, you don't really need to understand a lot of programming. There's something in the code called font size that should be an integer, and it's not. Okay. So let me go back through the code and see if I can find 9.5, a font size of 9.5. Now, one way to automate this, and you can do this with me, is I can use Control F. I think I introduced Control F last time. Control F for finding. So I hold down the control and press the F, and then I can just look for 9.5. I'll just look for 9.5. Okay, there it is. There's my bug. It does not want a font size that's 9 to 9. Not run from a model. Let's see. And this is a description of the variables. Maternal education. So this is going to be a categorical variable. The mother may have no education, primary education, secondary education, and higher education. Right? Wealth quintile. Quintile means that you divide the population into 5 classes. The lowest 20% is the first quintile, 20 to 40% second quintile, and so on. Urban means they live in the city. So this would be 1 or 0. 1 is urban, 0 is rural. Maternal age, I think that's clear. Birth order, okay. Number of children born to this mother. So it's the number of children before the current child. And then this is the label. Child died before 5. This is what we want to predict. So you can see that this is certainly an important practical problem. Try to determine children that are at risk of dying before age 5, depending on these variables. Okay. Because then you can target your interventions. All right, so let's go down. Okay. Okay. All right, now the cell here, I'm not going to talk about. This cell creates the data. This creates synthetic data. Now, in this tutorial, we're not concerned with creating the data. We just want to use the data. But this cell models actual data. So I'm just going to run it, and it will create data. Okay. All right. Now, it created the data. You should always look at your data before you start working with it. Don't just jump in and try to fit models. Look at the characteristics. See how it's arranged. See if the ranges of variables. See if there's any obvious relationship between variables. Plot histograms. Plot scatter plots. Do some exploration. You always look at your data beforehand. This way you can also find outliers or data that's not behaving properly. And then it gives you some indication how to treat with your data. Okay. All right. So how do I look at my data? What's that? Whoops. I need to fix this cell. All right. I think your cell is also not right. This is formatted as a text cell, but this should be a code cell. Remember, we have two different types of cells, text and code. Now, if I run this, nothing's going to happen because Python thinks this is a text cell. It does not recognize this as code. So I'm going to need to convert this cell to code. All right. How do I do that? Well, there's a couple of ways to do it. I think I'm going to go to Tools. Try to go to Tools. I'm going to go to Tools and Keyboard Shortcuts and see if this will give me a command that will help me convert this cell to a code cell. Right? So let me go to Keyboard Shortcuts and let's see. I just have to go scroll down and see if I can find one. Okay. All right. If you see it anywhere, let me know. Oh, there we go. Okay, good. Here we go. Control M, Y. So what this means is I press Control M followed by Y. Control M puts it in command mode. So you don't hold them all down at once. I'm going to go back. Whoops. I'm done with this. So I'm going to go back here. Click in the cell. You can see I do Control M and then Y. All right. Now this is evidently a code cell. You can see it has the run button. You can see it has the highlighted syntax. So it's quite easy to tell a code cell from a text cell. All right. And before executing, let's see what it's going to tell me. It's going to tell me the shape of the data set. We know that the data set is going to be a table with rows and columns. Okay. Now here you can see that it says DHS shape 0. This is the number of rows. Each row is a child. And the columns are the features. Okay. 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 And then here it's going to say, it says overall child mortality rate. You can see what it's doing. It's taking a mean. Okay. It's actually going to take a mean of the child died before 5 column. Okay. The syntax is a little bit complicated, but I think you can understand just by reading it. Okay. And then this one says urban-rural split, and it tells me how many, it's going to tell me the proportion that are urban. And then here it will actually print the first 5 rows of my data set. All right, so let's see what we have. We have 2,000 children, 7 columns. The last column is the label. The overall mortality rate is 11.5%. That was the average. And then here it says 38% urban. And here, this is the data set here. If I can pull it up. One of the challenges with this projector is that if I make it big enough to see, then it doesn't, if I can move this, I guess I can't. Okay. All right, it's not displaying very well. I think I have to click in here. There we go. There we go. Okay. So you can see the columns in the data set. This is the row number, child ID, maternal education. You can see the different categories, wealth quintile, urban, and so on. Okay. All right. Okay. That's some basic exploration. We should also plot some distributions. What's the shape of the data? All right. So here it's going to show let's see if there are any missing values. Now, in this case, there are values because it's simulated data. But in the real world, of course, you often have missing data, and you need to deal with that. Then this one gives the distribution of education. That's going to be a histogram. So here it's saying, it's giving you how different education affects the mortality rate. Okay. In some ways, you would expect higher education. Well, what do you expect? For higher education, do you expect a higher mortality rate or a lower mortality rate? Probably lower. Probably lower. But we can check and see if the data makes sense this way. Okay. Okay. We also have mortality rate by education. We could do mortality rate by wealth also. The mortality rate by wealth. Okay. So if I run this, I'm not sure if it will do a graph or just a table. This may just be giving me a table. All right. So we have a table here. So was it correct? Did we get lower mortality rate for higher education? Yeah, quite a bit lower. Quite a bit lower. 1/3. 1/3. That's really quite a bit lower. Now, this is an interesting graph here. Which quintile has the highest mortality rate? It's in a folder. No, it's probably not here. Those are my other folders. I'll find it at some point. Next time we'll find it. I can show you a very nice tool for finding files, but I don't want to get too distracted now. Okay. There's a very, very nice tool for finding files if you don't know where they are. I don't want this. Let's go back. All right, so let's look at the so you can see some different graphs. All right, this one we've seen already, child wealth. This one's new, maternal age at birth by child outcome. This is a little bit hard to interpret because you can see that it's just that maternal age of about 29 is when most children are born, and that's when you have the highest survival and the highest mortality. So you can see survival and mortality go together. Although this over here is quite interesting. Right. So you see some things that might be interesting. All right. All right, now, why is it doing that? I want to go back. Sorry. Okay, so let's go down. What's going on? All right, so now you can ask some question. Okay. Okay. All right. So this AI exercise, again, you can do this purely by AI. Right? And I think I showed you how you can do this. You just take the question, and paste it into your AI and ask AI to generate an answer. Okay. Okay. So for instance, this first question, if I wanted to have AI do it, and this is, again, this is what
very much, Professor Trump, for that wonderful session. A round of applause again for Prof for that wonderful session. We have some questions, so entertain some questions. Okay, we on. Someone will not give birth to question. I will take the number at 1. Okay, 2, 3. Guys, 4 from this side. Yeah, okay, 4 from that end. The 4 of you should come out and so I can get your quick. So the 4 persons are counted 1, 2, 3, and the 4th person. Please come so we can take your questions. I don't know, online, is there any questions online? Latif, if you check online for us, if there are questions online. All right, goodness, go on with your question.
So I warn you, I made to ask AI. But anyway, it was good for us to interact. Go ahead, please.
Thank you so much for the presentation. My question is, can a 99% accurate black box model because you mentioned about black box,
Yes.
using generative AI,
Okay.
can it be used for high risk accuracies?
Okay.
For example, this heart disease prediction.
Right.
What then should we be looking at? What type of challenges should we be looking at? Machine learning?
Okay. Well, I will cover that in the subsequent session. You need to know, choose your model. You also need to know how to evaluate your model. And you need to know how to interpret what's happening. So it's much more higher level. I like to say that with AI, everyone is a manager. AI is your employee. But you have to manage the AI. The AI can't manage you. So your part is more to make decisions and to look at outcomes and see how to apply them. That's something that AI will not do for you.
So the AI can help us with the idea of the code, why the decisions and the way we develop is now led for us.
So it, like she was, right? In the end, it's you who decide if you're going to implement some policy. AI can suggest, but you need to decide. I think it will also become more clear as we talk, as we go on to the subsequent session.
Thank you.
Good morning, sir. My name is great and a web developer. So I started running some machine learning projects for Department of Computer Science last year.
Okay.
So I found error when importing data. I've been added from Kaggle.
Okay.
Yeah, so I don't know, is there a way you can, like for many of us that might want to import data from Kaggle, like Kaggle website, because they get some.
Yes. Yes. Okay. All right. Yes. Okay. So the question is, he is getting data from a website called Kaggle. If you're, who has used Kaggle? Quite a well-known website for obtaining data. It's a good place to obtain data to develop models. And you're getting errors. Well, I really have found, sorry, I keep coming back to this, but I really have found that AI can be very helpful with this. You take AI, you paste the error into AI. Especially, I recommend Claude. Use Claude. Do you know Claude? Yeah, yeah. I really highly recommend Claude. Because what Claude does is the error you encountered, someone else encountered before. So Claude probably knows what to do. I don't know if you use Claude, but I've had great success using AI importing data. Yeah.
I'm also an AI expert. So once
Okay.
you notice that sometimes AI gets confused.
Sometimes.
Yes. Like I use it a lot to create
Okay.
sometimes when I'm lost in coding and
Okay.
sometimes it gets confused. So I have to use my own brain and my own knowledge to run it.
Okay.
So yes, because if relying on cloud, I found from reviews, I still see GPT better than cloud and
Okay.
Gemini because a lot
Okay.
of people give complaints that clouds don't really understand what
Okay.
you are. So you have been saying we should use AI. Yes, I'm a fan of AI, but most of the times it gets confused.
Okay.
Yes.
Sure. Of course. AI is not perfect, right? And you made a good point also that you typically you learn from experience. For your particular application, you may find one AI is better than another. That's true. Sometimes you take the output of one AI and put it into another AI to critique it. But you don't you don't treat uh, you don't treat AI as Bible, right? You have to critically evaluate what it gives you. Sometimes AI gives me something and I say, no, that's not right. But then but typically you can interact and get something better. And if Claude's not working for you, try something else. It's fine. Yeah. Yeah. Yeah.
All right, thank you very much,
Yeah.
Prof. So we are still having some few questions online questions. So Latif, you come up to read those questions for us. I'll take those questions online. 3 of us online.
Thank you so much, Prof. So we have a question here from Abdullahi Patsumota. So she's asking, do we take into account the complex sampling design of DHS survey in our ML model?
Okay. So, yes. Um, so again, it, that's a very broad question. This again is a place where you, have to do something. For instance, if I'm going to do a study, I would ask AI to give me a preliminary design. And then based on what I know, I might say, well, there's something wrong here, there's something wrong here, you need to adjust here, right? So it really depends on what kind of study you're doing.
We have another question. It's asking, in the decision tree, why does shorter bet interval show better survival? So we have like the interval split shows models that 29.8, so have 78% survival, but models that are less than 18.0 have 19% survival. So if shorter intervals increase risk, why does the tree show better survival for the shorter interval group? Are these different branches not in the same path? And if so, what distinguishes these subgroups?
Right. So we can look at all right. So this is a question about data interpretation, right? Let's go back and look at, I think the question is referring to this specific tree.
Yes.
So let me pull up the tree again and we can see what is happening. If I can find it, here we go. All right. So the issue is that,
Sir,
yes.
You are not sharing your screen.
Oh, I need to share. Okay, sure. Am I still connected? Oh, I am connected. Okay, good. Share my screen again. Actually, it's right here. Okay. All right. So, so you're saying that, I think they're saying less than 28.5, right? You can see that these final results relate to several decisions, right? This category here is maternal education less than 1.5, maternal age less than 28.5. So, and wealth quintile is less than 4.5. All right. So I think this is the highest rate category, the highest risk category. And what you can see is that in this category, the mothers have the least education, are the youngest, and have the least wealth. So tell me the question again. I'm not sure what they're referring to. Maybe you can bring it up here and I can read it.
Okay, so maybe I can hear you.
Sure. Okay. Yeah. It's right here. And chat should be here. It should be down here somewhere. I should be scroll up. Okay. Down, right. Okay. I think what happens is the mothers between 18 and 29 have poor survival. The children have poor survival. So it's only doing the larger category. Now, this does bring up a issue that you could increase the tree and have smaller categories. But then you run the risk of something called overfitting, where you have a model that works very well for the data you have, but cannot be generalized. So, suppose my answer to this question is that this statement, shorter intervals increase risk, is not a supported statement. And the other thing is that the graph that this person is referring to does not take into account education or wealth, which is also involved in the consideration. So, those are factors that are not included in the histogram that this person is referring to. But it does indicate something, as I mentioned before when we saw the histogram, that it seems very interesting that mothers less than 18 have such high child survival rate. And that may be worth investigating.
Okay, so there's another question from Tawemba Chibigo. Is there a certain amount of data required so that one can use
that can be used in ML? And the answer is yes. And the answer is more. You always want more data. There's never enough data. Now, so what I should say is that is that when you make a model, you should also evaluate its accuracy, right? You should also put error bars on the accuracy. All too many researchers develop a model and they say, oh, 90% accuracy, but they don't give error bars. It may just be that they got 90% accuracy by chance. So I will say that if you use ML with a small amount of data, you will get poor results. You will get poor results. The rule of thumb is that if you have little data, you want to use a simpler model. Okay? Because otherwise, if you use a very complicated model for little data,
For the wonderful session. It's a round of applause again for Professor Tron as he takes